Hi, I'm Vivek Kale, and I'm from Brookhaven National Lab. I'm going to talk with you today about my work on locality-sensitive loop scheduling within the SOLVE project in the exascale computing project. So before I go into detail on the scheduling strategies, let me start with providing you an overview of the U.S. Department of Energy's SOLVE project that this work is part of. SOLVE is a project that is used to develop OpenMP for DOE exascale supercomputers. It is a fork of the LLVM project. It's part of a large effort in the exascale computing project led by DOE, and one can link SOLVE's OpenMP implementation to their application program by downloading SOLVE OpenMP implementation at the GitHub link shown. It can also be used as a package on ECP systems like Summit by downloading it via SPAC. The SOLVE areas of impact are shown in this 3D cube figure below, and as noted, the SOLVE project aims at an OpenMP that provides for portability, productivity, and performance on ECP system. Moreover, one can see the key components as slivers in this SOLVE slab. The SOLVE slab particularly has a component of runtimes and compilers, and our runtime and our work that we are going to talk about today is in the main runtime system sliver, as well as partly the compiler sliver. Now with that, the diagram on the right shows the SOLVE software ecosystem, and one can more clearly see its engagement with applications, vendors, and the OpenMP ARB. Again, our strategies are focused in the compiler layer and the runtime layer. Let's motivate our strategies. Here's a caricatured outline of a typical scientific application program run on a supercomputer. The typical structure is compute, synchronize, and communicate through this MPI collective operation. Now, each time step here in this outer while loop contains the operations of loosely synchronous communication through these I send, I receive waitals, and then a computation, and then a collective operation through this collective op. And now what you might see is often there's many interleavings of these types of compute-communicate patterns in a real application. So to ensure that the application's performance is good at scale, there's this red inner loop that needs to be particularly well performing. And in particular, it needs to be distributed well across the processing elements of a node, and that involves loop parallelization. That loop parallelization should distribute the work across processing elements in a near uniform way, and it should do so as efficiently as possible. So how do we do near perfect work distribution within a node? Well, we need to focus here on this computation region, and we focus in on by parallelizing using OpenMP, particularly the OpenMP parallel work sharing clause. The key thing here is that we use the schedule clause on the work sharing directive, and that allows us for varying how we redistribute the work across cores or across processing elements. With this, we show our key approach of low overhead or locality-sensitive loop scheduling. The goal underlying the low overhead scheduling strategies is to efficiently mitigate within node load imbalance of a parallel loop. And the core idea behind our low overhead scheduling strategies is shown in the bottom diagram here. And that is that each thread first executes some number of pre-assigned loop iterations statically, shown in blue, and then immediately continues to retrieve the remaining loop iterations from a work queue shared among threads. And these iterations are dynamically executed loop iterations. So we refer to the total number of pre-assigned loop iterations across all threads or cores or processing elements as the static fraction. We refer to the remaining number of dynamically allocated loop iterations as a dynamic fraction. And whatever method is used to determine the dynamic fraction for a particular OpenMP loop, having this ability to tune the dynamic fraction enables these locality-sensitive and low overhead scheduling strategies that maximize load balance and minimize data movement. We applied this strategy to a dense linear algebra code, and it is currently part of the ECP application library called Slate. What we've done is split the communication, a LU factorization into two parts, a static part and dynamic part, and then tune the dynamic fraction. And by doing so, we get a significant performance improvement over Intel MKL. We see that through the results on the left. We also see on the results on the right, that is the histogram diagram, that the performance variability of using a mixed static dynamic scheduling scheme is reduced, and that improves the scaling when you run this code on millions of nodes. A paper was published on this work with my collaborator Simply Stunfact, and I've shown the citation here. With that, we have used a similar approach for improving locality through the use of Affinity Hints. And in particular, we use Affinity Hints for a task loop for loop. So it's similar to the regular parallel for with schedule, except it just breaks down the loop into tasks rather than chunks. And we experimented with this idea on two application codes. One is a generalized matrix multiplication code, and the other one is a Jacobi 2D. What we experimented with are different metrics. So we show the plot on the two left plots show raw execution time and the cache traffic volume. And what this shows is that for just the Jacobi 2D, the Jacobi 2D has a significant sensitivity to using the locality-aware scheduling scheme, and it has a more significant sensitivity when we have larger problem size. The interesting thing, though, to really see is actually the lower energy consumption shown on the right. We see that both the matrix multiplication and the Jacobi 2D are actually consume less energy on the processor than their baseline counterparts. Now, with that, we shift our attention to the heterogeneity of the nodes on supercomputers, particularly exascale supercomputers that DOE is providing. Systems like Summit have about 6 GPUs per node, and about 90% of their computational power on the node is from the GPUs. So it's important to make use of these GPUs efficiently. So we have worked on an approach recently in which we use OpenMP to parallelize across the GPUs, and then on top of that, use dynamic load balancing across those GPUs through OpenMP's constructs, task loops, and target. We found actually a very timely application in the last several months, particularly a molecular docking code called AutoDock, which is currently being used on Summit to identify potential vaccines for the disease COVID-19. So for this, we created a mini app to study our approach for OpenMP based on for first single GPUs, and then we extended that to a multi-GPU mini app. What we see on this slide on the right here is a plot. The lower, the x-axis is the computation number or target region number, and the y-axis is the time. And we see this large number of fluctuations in the computation number. And that is indicative of the large load imbalances of each task. So here, the real question is, how do we mitigate the load imbalances across the GPUs? We talked about across cores before, but now we need to treat the multiple GPUs as a multi-GPU, just like a multi-core. We start with an OpenMP offload code using one GPU, and then we extend the code for multiple GPUs by having a task loop surround the key computational loop, and the task loop bucket, the task loop tasks are shown in those red buckets. From that, we have a task queue distributing those tasks to each of the CPUs. From that, we have the CPUs have a shared queue that represents which GPUs are ready to execute one of their own tasks. And then when a CPU finds a GPU in that shared ready queue, it acquires that GPU, then launches the next task and holds a signal or a flag until the GPU has finished computing that particular task. So this is the method that we use for assigning these several tasks to the multiple GPUs on a node. So question is now, how does the application programmer actually use our strategy? Well, this is what the code on the left shows what they do to modify their application code. And I'll just point out that the task loop here is that task loop I showed, and it's parallelizing these tasks across CPUs. Then each CPU is identifying, hey, which GPU do I run on? And so there's a function for that, and that function calls this larger scheduler function, and that function contains the shared array of GPUs that are ready. Specifically, it's this occupancies array. Then once it's found the GPU to run on, it sets the success flag, and then immediately goes to run off or offload the computation that's given to device dev, and it does so by using the device clause in OpenMP. Then this is the core computational work of the application. Then once this computation is done, that thread, the CPU, which is managing a thread, will set the occupancies array back down to for that particular device back down, and that signals that, hey, this GPU is ready. With that strategy, we show this mini app experimented with different scheduling strategies, and we also compare it with an MPI version. That is where we use MPI to parallelize across GPUs, And then within that, we have OpenMP to do the offloading. That is actually one can say a conventional way that one parallelizes across GPUs today. But the drawback of doing that, of course, is that you can't make use of OpenMP's load balancing capabilities. So what we are doing here in this experiment, our key question is, can we do better than this conventional way of parallelizing across these multiple GPUs? We can see in the blue, ignore the no patch, this blue here is showing the MPI version, the execution time. Then ignore again the static no patch. The static here is just the static mapping of these target regions to GPUs. And then we have a randomized selection of GPUs. So randomized, each thread chooses a random GPU to run on. And then this is just each thread chooses the next GPU in a cycle. Actually, and both of these already show performance improvement over the baseline of our original static, and a very slight improvement over MPI, but we want to point out that the real improvement comes from when you use dynamic scheduling, which we just highlighted and outlined in a previous slide, and that provides just about a 2x performance improvement. We also had an optimization over dynamic where we have these multiple queues. So we reduced data movement across GPUs. That actually improved our performance even more. And so it improves just over 2x over MPI and actually a little more over the static version. I'll just note that the no patch here just means that we had actually started with, we used the latest LLVM fork for all of our experiments, the latest solve fork of LLVM for all our experiments. And so we are actually using the most optimized version of solve with all the compiler optimizations and those are helping for the target offload region. But the real improvements are seen in this through dynamic scheduling. With that, I will go to some proposals of extensions of OpenMP based on these low overhead scheduling strategies and TaskToGPU scheduling strategies. We have here a glimpse of how a proposed user-defined scheduling strategy will work through a particular interface in which a user declares a new schedule. Here we call it the users called it myDin, and then they associate three functions: basically an onQueue function, a dequeuing function, and an end function, an affinity function. The onQueuing is really the start function, the dequeue is next, and the end is fini. And then they use that declaration of the schedule as the hook or the identifier in the parallel for schedule shown in the blue here. Then with that, they can also have their own parameters. So now you don't just need a chunk size, you can actually have your own set of, a user can make their own parameters to the loop scheduling strategy. This is important, particularly for our tunable loop scheduling strategies where we had the static fraction. And so now you can actually put the static fraction in as one of these parameters. You can also put other parameters like perhaps a distribution of task sizes in a task queue distribution, and those could be exponentially decreasing or decreasing through another rate. The key thing is that the compiler, instead of calling into the runtime library for loop scheduling, it's going to invoke these functions that the user defines within source code. And typically this is going to be a power user that helps the full application programmer to define a real loop schedule. Work was published in 2019 IWAMP on an interface for this. This shows just a little more detail on how the user-defined schedules mechanics would work. You can see here on the right the application code, and on the left it just goes into a little more detail on what those functions, those onQ and DQ functions and Affinity functions look like. I add them just to mention here, but you can look online for more details. The second proposal is more for the TaskToGPU scheduling strategies, and that actually builds on the user-defined scheduling strategies. And it's important to note that the user-defined scheduling schedules can work on are mainly for the CPUs, but the proposal itself is not restricted to CPUs. You can have user-defined schedules that work across GPUs. So the point that I want to make is that here in our target scheduler proposal, which allows for tasking across multiple GPUs, so it's CPU task to GPU scheduling strategies, we have a new construct called target scheduler, and that dictates the inner task loop or the parallel for to distribute work from CPUs to GPUs in the manner that I described previously in that sketch. And it will do so that the load balancing is improved as best as possible. And I'll just note one other thing is the affinity clause here. We've also proposed this. This actually works, is relevant for, there's also actually already as affinity clause for CPUs in the standard in OpenMP 5.0, but for our proposal, we're actually proposing this for the TaskToGPU scheduling. So this is also part of our proposal. And affinity clause is a hint to improve data locality. And so we've already shown that data locality is important, particularly this affinity is important for results with the Jacobi code and the matrix multiplication code, not just for performance, but also for energy efficiency. Now, I would like to just briefly talk about making our code for user-defined schedules and locality-sensitive scheduling more performance portable. So this is the original code here, and we see that this uses explicitly lightweight scheduling. But then what we have is a Raja implementation with the policy with OpenMP lightweight scheduling, and that improves, that gives a more performance portable version here through this Raja inlining. And then we have all this is the key application code that the scientific application programmer would use. So this is what happens now is that the lightweight scheduling is calling this code, and now we have a more easy to use locality sensitive scheduling strategies, and it improves portability. So with that, we also investigate now that there's load imbalances both across and within node. And so we used LLNL's Lassen to identify some of these load imbalances. And this is courtesy work with Harshita Menon and other members at Lawrence Livermore Lab, including Brian McCandles. The key thing is that the diagrams here show red hot spots showing across node, both across node and within node load imbalance on the top and bottom. And so to identify given this identification of the problem, we actually just looked at a solution to have this synergistic load balancing and loop scheduling. So that involved using an existing runtime system that had cross-node load balancing and augmenting it with within node loop scheduling, and then synergizing it together so that we would have this mechanism that improved performance both through these two complementary techniques. And this resulted in a poster which was at SE17, which is also nominated for a Best Poster. So then here's some related work. We'll go into details. These are important pieces that go in that have done similar work on low overhead loop scheduling, though none of them have done the tunable aspects and gone into any detail on locality. With that, we have some future directions, and those are to namely continuing to create examples of user-defined schedules using an existing user-defined schedule LLVM OpenMP reference implementation. And then we're also going to work on task improvements for tasking of GPUs, and that will include the TaskToGPU scheduling strategies and locality strategies as outlined earlier through our prototype. We're going to be in the next year for the in preparation for the OpenMP 6.0 release, which is in FY 2023. We will be looking at the task to multi-GPU scheduling and user-defined schedule proposals and trying to push those in. And also a long-term goal is to upstream our implementations into LLVM. And then finally, we're going to work to develop libraries that are beneficial for heterogeneous nodes, particularly libraries that interact with the cross-node load balancing libraries like Charm++, and also they also performance portability libraries, in particular Raja, as well as another one that's Cocos. Thank you for listening to my talk, and I will invite you to see more of our work on the OpenMP website by going to openmp.org.